Hello, in this lecture we'll find out the area of the green shape. In the drawing we have a circle. The radius of this circle r equals to 2 units. In addition, we have inside this circle peripheral angle ACB. This is peripheral angle ACB that is equals to 70 degrees in its size. And we also have the common external point P. From this common external point P, we have two tangents to this circle, tangent PA and tangent PB. And our mission is to find out the area of this green shape. Point O is the center of this circle, so we join points O and B together by a straight line. Point O is the center of this circle, point B is the point on the circle itself, therefore 97 OB is the radius of this circle that is equals to 2 units in its length according to what is given us the question. So the radius R equals to 2. So I can implement here rule 1. According to rule 1, a tangent to the circle is perpendicular to the radius drawn to its point of tendency. So in the drawing we have a circle and we also have tangent AB that is tangent to this circle here at point M. And we have the radius OM that is drawn to point M, that is the point of tendency of tangent AB with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius MO. If AB is perpendicular to MO, it means that this angle equals 90 degrees, this angle also equals to 90 degrees. According to this rule, rule 1. So we can actually implement rule 1 in our drawing. Why? Because in our drawing we have the radius OA of this circle that is drawn to point A, that is the point of tendency or tangent PA with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent PA will be perpendicular to the radius OA. If PA is perpendicular to OA, it means that this angle equals to 90 degrees. Likewise, according to the same rule 1, we have the radius OB that is equal to R. The radius OB is drawn to point B, that is the point of tendency of tangent PB with this circle. And whenever we have a radius that is drawn to the point of tendency, then tangent PB will be perpendicular to the radius BO. If PB is perpendicular to BO, it means that this angle equals to 90 degrees, according to the same rule, rule 1. In the next step, I will present to you a new rule and we will implement the new rule in our drawing. According to the new rule, that is rule 13, the central angle is twice as large as the peripheral angle subtended on the same arc. Okay, again, rule 13. the central angle is twice as large as the peripheral angle subtended on the same arc. So in the drawing we have a circle. Inside this circle we have peripheral angle ACB is equal to 30 degrees in its size, and its peripheral angle ACB is subtended on this arc RKB. And we also have the central angle AOB. This central angle AOB is subtended on the same arc RKB. So according to this rule 13, the central angle AOB will be twice as large as the peripheral angle that is subtended on the same arc RKB. And because of the fact that the peripheral angle ACB is equal to 30 degrees in its size, the central angle AOB must be equal to 2 theta, because it is also subtended on the same arc RKB. Okay, so the central angle is almost twice as large as the peripheral angle that is subtended on the same arc. In this drawing, the central angle AOB is subtended on the same arc as the peripheral angle ACB. And because of the fact that the central angle ACB equals to theta, therefore the central angle AOB, this central angle AOB must be equal to 2 theta, because it is also subtended on the same arc RKB, on the same arc as peripheral angle ACB. Okay, so we can actually implement rule 13 in our drawing. Why? Because in our drawing we have peripheral angle ACB. This is peripheral angle ACB that is equal to 70 degrees in its size, and it is subtended on RKB. Therefore, the central angle AOB that is subtended on the same arc RKB will be twice as large as the peripheral angle ACB. And because of the fact that the peripheral angle ACB equals to 70 degrees in size, therefore the central angle AOB must be equal to 70 degrees times 2, that is 140 degrees. So therefore, according to rule 13, the central angle AOB must be equal to 140 degrees, because it is also subtended on the same arc RKB as the peripheral angle ACB. In conclusion, found out that according to rule 13, the central angle AOB is equal to 140 degrees in its size. So I write it down. Central angle AOB equals to 140 degrees in its size. In the next step, we join points O and P together by a straight line. By joining points O and P, we created here two right triangles. The upper right triangle, triangle AOP, and the lower right triangle, triangle POB. So in the next step, we will prove that the upper right triangle AOP is congruent to the lower right triangle, triangle POB. So write it down. We'll prove that the upper right triangle, triangle AOP is congruent to the lower right triangle, triangle POB. So those two right triangles can go into each other. First of all, side AO of the right upper triangle AOP is equal to side BO of the right lower triangle, triangle POB, plus both of those two sides are the other of the circle, therefore they are equal to each other. So OA, side OA of the right upper triangle equals to side OB of the right lower triangle repeat again, OA equals to OB, they are both the radii of the circle, that is equal to 2 units, therefore they are equal to each other. In addition, side OP is a common side that belongs to both triangles, so we can write down that OP equals to itself. It's a common side that belongs to both triangles. Repeat again, side OP equals to itself is a common side that belongs to both triangles. And finally, side PA of the right triangle, the right upper triangle APO is equal to side PB of the right lower triangle POB. So PA equals to PB PA equals to PB according to rule 2. Repeat quickly on rule 2. According to rule 2, the length of two tangents from a common external point to a circle are equal. So in the drawing we have a circle and we have the common external point, point P. From the common external point, point P, we have two tangents to this circle, tangent PA and tangent PB. And according to this rule 2, they are equal to each other. That is to say, PA equals to PB. In the drawing of the question, we have the common external point, point P. From the common external point, point P, we have two tangents to this circle, tangent PA and tangent PB. According to rule 2, they are equal to each other. That is to say, PA equals to PB. Okay? According to rule 2. So actually prove that all the three sides of the right upper triangle POA are correspondingly equal to all the three sides of the right lower triangle, triangle POB. Therefore, those two right triangles can go into each other according to side rule. So I write it down. The right upper triangle, triangle POA is congruent. This is the sign of congruent to the right lower triangle, triangle POB. According to side rule. And from the fact that those two right triangles can go into each other, we derive that those two angles are also equal to each other. That is to say, angle AOP of the right upper triangle AOP is equal to this angle. It is actually angle BOP of the right lower triangle BOP. And they are equal to each other according to the rule that corresponding angles in congruent triangles are equal to each other. Those two triangles congruent to each other, therefore the two corresponding angles, those two corresponding angles must be also equal to each other. So if we define the upper angle as alpha, then the lower angle must be also equal to alpha because they are equal to each other. So if one of the also equals to alpha, the other angle must be also equal to alpha. So actually alpha plus alpha is this angle that is 140 degrees. Okay, alpha plus alpha equals to 140 degrees. So I write it down. So 2 alpha equals to 140 degrees. We divide this equation by 2. And finally we get that the missing angle alpha equals to 140 degrees over 2, that is 70 degrees. So actually this angle is angle alpha is equals to 70 degrees in its size. And this is also angle alpha that is equals to 70 degrees. In the next step, we'll focus on this upper triangle AOP. In the right upper triangle AOP, tangents 70 degrees. Is equals to AP over AO. Again, in the right upper triangle AOP, triangle 70 degrees equals to AP over AO. Tangent 70 degrees is 2.75 and it is equals to AP. AP is the missing side, so we leave it as it is, over AO. AO is the radius of this circle that is equal to 2. R equals to 2, so we substitute AO by 2. So in conclusion, we found out that 2.75 equals to AP over 2. Here we multiply this equation by 2. And we get that AP equals to 2.75 times 2. It's actually 5.5. So in conclusion, we found out that AP equals to 5.5 units in its length. So this side AP of the right triangle AOP is equals to 5.5 units in its length. Our mission is to find out the area of this green shape. So what is the area of this green shape? from the drawing, it is very easy to see that the area of this green shape equals to the area of the right upper triangle, triangle AOP. Plus the right lower triangle, triangle BOP. So actually, the sum of the areas of those two right triangles will give us the area of this quadrilateral AOBP. So the area of quadrilateral AOBP minus the area of this sector AOB will give us exactly the area of this green shape. So I repeat again. Actually, found out that the area of the green shape equals to the area of the right upper triangle AOP plus the area of the right lower triangle BOP. The sum of the areas of those two right triangles will give us the area of quadrilateral AOBP, and then we have to subtract from the area of the quadrilateral AOBP the area of sector AOB. Here the round line around AOB is the same for the sector, it means sector AOB, and the square brackets is the same for the area. So in total this expression equals to, it is the area of sector AOB. The area of this sector AOB. Repeat again that the area of this green shape equals to the area of quadrilateral AOBP, that is the area of the right upper triangle AOP plus the area of the right lower triangle BOP minus the area of this sector AOB will give us exactly the area of this green shape. Okay. So in the next step I will clarify and explain what is a sector, so a sector is a portion of a circle, or a sector is part of a circle. So here in the drawing we have a circle, and the green shape AOB is a sector. The green shape AOB is sector AOB. So sector AOB consists of the two radii of this circle, the radius AO and the radius BO, and the arc AB between those two radii. So the radius AO is one leg of this sector, the radius BO is the second leg of this sector, and we have also the arc AB, that is actually the arc between the legs BO and AO. Okay, so a sector is like a pizza slice. Okay, and the angle between the legs AO and BO of the green sector AOB is angle theta. So the area of this sector AOB is equal to the area of the circle that contains the sector, that is pi r squared, because the radius of the circle is r, times theta, that is the angle between the legs AO and BO of this green sector AOB, over 360 degrees. I repeat again, the area of this sector AOB equals to pi r squared, that is the area of the circle that contains the sector, times theta, that is the angle between the legs of the sector, over 360 degrees. In conclusion, we found out that the area of this sector AOB is equal to pi r squared times theta over 360 degrees. Okay. So the area of the green shape equals to the area of the right upper triangle AOP plus the area of the right lower triangle BOP minus the area of sector AOB. We found out that those two right triangles can go into each other, and therefore they have also the same areas. So the area of the right upper triangle AOP is equal to the area of the lower right triangle BOP. Therefore we can substitute the area of this right lower triangle BOP by the area of this upper triangle AOP because they have the same areas. We do it now and we get that the area of the green shape in total will be equal to the area of the upper right triangle AOP plus the area of the right lower triangle BOP. So we substitute the area of the lower right triangle BOP by the area of the upper right triangle AOP. Minus the area of sector AOB. So the area of the green shape in totality equals to the area of the upper right triangle AOP plus the area of the upper right triangle AOP, that is 2 times the area of the upper triangle AOP minus the area of sector AOB. So first of all, we have to find out the area of the upper right triangle AOP. We multiply it by 2, and then we subtract the area of sector AOB from 2 times the area of the right upper triangle AOP, and this will give us the area of the green shape. So what is the area of the right upper triangle AOP? We know that the area of any triangle equals to the base of the triangle times the height to the base over 2. So we choose the base of this right triangle AOP. The base of this right triangle AOP is AO, side AO, times the height to the base. The height will be AP because it's created 90 degrees with the base AO. So the height is AP over, to repeat again, the base of the right upper triangle AOP is AO, the height to the base is AP over 2. AO equals to 2 units, it is the radius of the circle, times AP, AP is 5.5 units, over 2. So we have 2 in the numerator and 2 in the denominator, so 2 will get cancelled, and we left only with 5.5. In conclusion, we found out that the area of the upper right triangle AOP is equal to 5.5 square units. and the area of the green shape in total equals to 2 times the area of the right upper triangle AOP. That is actually 2 times 5.5, that is 11, minus the area of sector AOB. So we just have to find out the area of sector AOB, and 11, that is the area of quadrilateral AOBP minus the area of sector AOB will give us exactly the area of the green shape. So in the next step we will find out the area of this sector, sector AOB. So what is the area of sector AOB? The area of sector AOB equals to the area of the circle that contains the sector, that is actually pi r squared, times the angle between the legs of this sector, that is actually 140 degrees, as you can see here, 140 degrees over 360 degrees. The radius of this circle r equals to 2, therefore r squared is 2 squared, that is 4. So the area of the circle that contains the sector is 4 pi times 140 degrees over 360 degrees. So this expression in total it is equals to 4.888 square units. In conclusion, we found out that the area of sector AOB is equals to 4.888 square units. And the area of the green shape in total, we already found out that the area of the green shape is equals to 11, that is the area of quadrilateral AOBP minus the area of sector AOB. So AOBP is the area of this sector, 11 is the area of this quadrilateral AOBP minus the area of sector AOB, that is 4.888 square units. And 11 minus 4.888 is 6.111. In conclusion, we found out that the area of the green shape is equals to 6.111 square units. This is again the area of this green shape is equals to 6.111 square units. So in the next step I will summarize the lecture. In this lecture, I found out the area of this green shape. So, in the drawing, we have a circle. You know that the radius of this circle r equals to 2. Inside this circle, we have peripheral angle ACB that is equals to 70 degrees in its size. In addition, we have here the common extreme point P. For the common extreme point P, we have two tangents to this circle, tangent PA and tangent PB. And our mission is to find out the area of this green shape. So first of all, we join points O and B together by a straight line. Point O is the center of the circle, point B is the point on the circle itself. Therefore, line segment OB is the radius of this circle that is equal to R. Here, we implemented rule 1. We have the radius OA that is down to point A, that is the point of tendency of tangent PA with this circle. And whenever we have a radius that is down to the point of tendency, then tangent PA will be perpendicular to the radius OA. If PA is perpendicular to OA, it means that this angle equals 90 degrees. According to rule 1, likewise according to the same rule 1, we have the radius OB that is down to point B, that is the point of tendency of tangent PB with this circle. And whenever a radius that is down to the point of tendency, then tangent PB will be perpendicular to the radius BO. If PB is perpendicular to BO, it means that this angle equals to 90 degrees. Okay? Then I presented to you a new rule, it is actually rule 13, and we implemented rule 13 in our drawing. According to rule 13, the central angle is twice as large as the peripheral angle subtended on the same arc. Repeat again on rule 13. According to rule 13, the central angle is twice as large as the peripheral angle subtended on the same arc. So in the drawing, we have a circle. Inside this circle, we have the peripheral angle ACB that is equal to theta, and this peripheral angle ACB is subtended on arc AB. In addition, we also have the central angle AOB that is subtended on the same arc AB. Therefore, according to this rule 13, the central angle AOB must be twice as large as the peripheral angle ACB that is subtended on the same arc AB. And because of the fact that the peripheral angle ACB equals to theta, the central angle AOB that is subtended on the same arc AB will be equal to theta. Okay. We can actually implement rule 13 in our drawing. Why? Because in our drawing we have peripheral angle ACB is equal to 70 degrees in its size, and this peripheral angle ACB is subtended on this arc AB. And we also have the central angle AOB that is subtended on the same arc AB. Therefore, the size of this central angle AOB must be twice as large as the peripheral angle ACB that is subtended on the same arc AB. And because of the fact that the peripheral angle ACB equals to 70 degrees, the central angle AOB that is subtended on the same arc must be equal to 70 degrees times 2, that is 140 degrees. In conclusion, found out that the central angle AOB, this central angle AOB equals to 140 degrees in its size. In the next step, we are going together points O and P. By joining points O and P, we can get here those two right angles, the upper right angle AOP and the lower right angle OBP. And then we proved that those two right angles can go into each other according to side rule. So I repeat quickly on the proof. Why those two right angles can go into each other? First of all, side AO of the right upper triangle AOP equals to side BO of the right lower triangle BOP. They are both the radii of this circle, therefore they are equal to each other. Repeat again, AOA equals to OB. They are both the radii of the circle that is equal to 2, therefore they are equal to each other. In addition, we have side PO, that is the common side that belongs to both triangles, so you can write down that PO equals to itself as the common side that belongs to both triangles. So repeat again, PO equals to PO as the common side that belongs to both triangles. And finally, side AP of the right upper triangle AOP equals to side BP of the right lower triangle BOP, according to rule 2. PA equals to PB according to rule 2. So, I repeat quickly on rule 2. According to rule 2, the lengths of two tangents from a common standpoint to a circle are equal. So in the drawing we have a circle and we have the common standpoint point P. From the common standpoint point P we have two tangents to this circle, tangent PA and tangent PB. And according to this rule 2, they are equal to each other. That is to say PA equals to PB. Actually, we implemented rule 2 in our drawing. In our drawing we have the common standpoint point P. From the common standpoint point P we have two tangents to this circle, tangent PA and tangent PB. And according to rule 2, they are equal to each other. Again, PA equals to PB according to rule 2. So actually prove that all the three sides of this right upper triangle AOP are correspondingly equal to all the three sides of the right lower triangle, triangle BOP. Therefore, those two right triangles can go into each other according to side rule. Okay. Yeah. The upper triangle AOP can go in. This is the sign of congruent to the right lower triangle BOP according to side rule. And from the fact that those two right angles can go into each other, we derive that those two angles must be also equal to each other. This is to say, the right upper angle AOP is equal to the upper angle AOP is equal to the lower angle BOP according to the rule that corresponding angles can go into angles are equal to each other. Those two right angles can go into each other. Therefore, those two angles must be also equal to each other because they are the corresponding angles. Okay, so if this angle is alpha, then the other angle also must be equal to alpha because they are equal to each other. So if one of those two angles is equal to alpha, then the other angle must be also equal to alpha because they are equal to each other. From the drawing, it is very easy to see that alpha plus alpha in total it is equal to this angle that is 140 degrees. So alpha plus alpha equals to 140 degrees. Alpha plus alpha equals to 140 degrees. That is to say 2 alpha equals to 140 degrees. We divided this equation by 2 and finally found out that the missing angle alpha equals to 140 degrees over 2, that is 70 degrees. So this missing angle alpha equals to 70 degrees inside, and this is also angle alpha that is equals to 70 degrees. In the next step, we focus on this right upper triangle, triangle AOP. In the right upper triangle AOP, tangle 70 degrees equals to AP over AO. Again, tangle 70 degrees in the right upper triangle AOP is equals to AP over AO. Tangle 70 degrees in the right upper triangle AOP equals to AP over AO. Tangle 70 degrees is 2.75 and is equals to AP. AP is the missing side, so we leave it as it is, over AO. AO is the radius of this circle is equal to 2, so we substitute AO by 2. In conclusion, we found out the 2.75 equals to AP over 2. Here we multiply this equation by 2 and finally found out that AP equals to 2.75 times 2, that is 5.5. In conclusion, we found out that the missing side AP equals to 5.5 units in its length. Our mission is to find out the area of this green shape. So what is actually the area of this green shape? From the drawing it is very easy to see that the area of this green shape equals to the area of the right upper triangle AOP plus the area of the right lower triangle, triangle BOP. The sum of the areas of those two right angles will give us the area of quadrilateral AOBP. And after we subtract from the area of this quadrilateral AOBP the area of this sector AOB, we get exactly the area of this green shape. Repeat again. the area of the green shape in total equals to the area of the upper right triangle AOP plus the area of the lower right triangle BOP. So the sum of the areas of those two right triangles will give us the area of quadrangle AOBP. And then after we subtract the area of sector AOB from the area of quadrangle AOBP, we get exactly the area of this green shape. But because of the fact that we have already found out that the right upper triangle AOP is congruent to the right lower triangle BOP, they also have the same areas. Therefore, we can substitute the area of the right lower triangle BOP by the area of the upper triangle AOP. We actually did it, and here, the area of the green shape in total equals to the area of the upper right triangle AOP plus the area of the lower right triangle BOP. We substitute the area of the lower triangle BOP by the area of the upper triangle AOP minus the area of sector AOB. So the area of the upper right triangle AOP plus the area of the upper right triangle AOP equals to 2 times the area of the upper right triangle AOP minus the area of sector AOB. So first of all, we have to find out the area of the upper right triangle AOP. The area of the upper right triangle AOP equals to the base of the area of any triangle equals to the base of the triangle times the height to the base over 2. So here, in the right upper triangle AOP, we choose the base as AO, and the height to the base is AP. Why? Because AP creates 90 degrees with the base AO. Open again, the base of the right upper triangle AOP is AO, and the height to the base is AP, divided by 2. AO is 2, it is the radius of the circle that is equal to 2 units. AP is 5.5 over 2. So here we have 2 in the numerator and 2 in the denominator, so 2 will get cancelled, and left only with 5.5. In conclusion, we found out that the area of the upper right triangle AOP is equals to 5.5 square units. Okay, the area of this upper right triangle AOP equals to 5.5 units. So 2 times the area of this right triangle equals to the area of quadrangle AOBP. Okay. 2 times the area of the right upper triangle AOP equals to 2 times 5.5, that is 11. So in total, we actually found out that the area of this quadrangle AOBP equals to 11 square units. So the area of quadrangle AOBP, that is 11, minus the area of this sector AOB, will give us exactly the area of this green shape. So in the next step, we actually found out that area of this sector AOB. I think quickly on the concept of sector. Sector is part of a circle. Here, the green shape AOB is a sector. Sector AOB consists of 2 legs, AO, that is the radius of the circle, and BO is also the radius of the circle, and the arc between those 2 radii, that is AB, and the angle between the legs AO and BO of this sector AOB is theta, and the area of this sector AOB equals to pi r squared, that is the area of the circle that contains the sector, times the angle between the legs of this sector, that is theta, over 360 degrees. In conclusion, we found out the area of this sector AOB equals to pi r squared, that is the area of the circle that contains the sector, times theta, that is the angle between the legs of the sector, over 360 degrees. So pi r squared times theta over 360 degrees equals to the area of the sector. So therefore, the area of this sector AOB, according to the formula that I presented to you, will be equal to pi r squared, that is the area of this circle that contains the sector AOB, times theta, that is 140 degrees, it is the angle between the legs of this sector AOB, that is 140 degrees over 360 degrees. I repeat again, the area of sector AOB equals to pi r squared, that is the area of the circle that contains the sector, times the angle between the legs of the sector, that is 140 degrees over 360 degrees. So the area of sector AB equals to pi r squared. R is 2, therefore r squared is 2 squared, that is 4. So in total, the area of the circle that contains the sector equals to 4 pi times 140 degrees over 360 degrees. So 4 pi times 140 degrees over 360 degrees, in total it is equal to 4.888 square units. In conclusion, found out that the area of this sector AOB equals to 4.888 square units. And we have already found out that the area of this ring shape in total equals to the area of quadrangle AOBP, that is the sum of the areas of those two right angles, minus the area of this sector, sector AOB. And the area of quadrangle AOBP equals to 11 square units, and we just right now found out that the area of sector AOB is 4.888. So 11 minus 4.88 is 6.111. And we found out that the area of this ring shape equals to 6.111 square units. Okay, thank you very much.